Okay, let's get started. So welcome to 677, Distributed and Operating Systems Spring 2014. Today's lecture is going to be mostly introductory. And I will talk about the syllabus, give a quick introduction to what are distributed systems and what we are going to cover in this class and why distributed systems are important for us to study. Okay, and then starting next time, we are going to actually delve into the various topics that we are going to cover in this course. So the course is being recorded. As I sent out an email, as I said in the email that I sent out, there are two sections of this class. This is the classroom section. There's an entire other section of students who are following along online, and I record the lectures in order to help them keep up with the class material. The recorded lectures will also be available to you in this class. So if you miss some lecture or have to go back, review it, you will have the opportunity to do so. This is not a reason to stop coming to class. I think there are some useful things you can achieve by coming to class and ask questions and so on as well. So keep that in mind. So let me just begin with some course logistics and administrative details. Everything that I cover in the class will also be made available, like the lecture slides, lecture notes, recordings. They will all be put up on the course web page, which is here. Okay. There is also a Moodle site for the course. We will be using Moodle mostly for you to turn in assignments. Okay, so you don't have to hand in paper copies, you simply upload it onto Moodle and you will be given your grades back through Moodle. Okay, lecture materials will be here and assignments and exams, not exams, but programming assignment homeworks come in through Moodle. Okay, so keep that in mind. There are two other course staff who you should be aware of. There's the TA, Tian Go. I will have her come to class to introduce herself to you. She is out of town and should be back today. So next class I'll have her come in and just introduce herself. She will handle the lab aspects of the course in terms of grading the lab, providing help on the lab, and so on. Of course, I am here to help as well, but she will handle some aspects of the lab. Okay. Her office hours and so on, I will announce as soon as I have it from her. There's also a grading assistant who you probably won't encounter a whole lot, but he'll be doing some of the grading for the homeworks that you will be turning in. Okay, but I just wanted you to know that there are two staff who will be associated with the course. Both Tian and I will have office hours every week. Okay, my office hours will be on Mondays right after the course lecture, and you can always make an appointment to come see me on other days. Okay. Tian has yet to give me her office hours, but I am assuming hers will be on Wednesday and Friday. Okay, so 3 days of the week there will be someone to come and talk to if you have questions. Okay. Okay, so I will go through the course outline, talk about the textbook and so on. Okay, so the course has several key topics. We will use a textbook which is Distributed Systems by Tannenbaum. Okay. There will be a copy of this book also put on the reserve in the library. So if you don't want to buy the book, you could potentially get by just using the library copy, using the course notes and so on. But if you want to buy it, that's fine as well. I haven't asked the textbook annexer to get a copy of the book because most of you find better prices elsewhere. So feel free to go and buy a used copy or some such thing if you want to get one. Okay? It's the second edition of the book that is the textbook, not the first edition. Okay? So the course outline which I have here roughly follows what's in the book. Okay, so today we'll talk about what is a distributed system, and I'll give you an overview of the topic. Okay, and then we'll talk about architectures for distributed systems. Then we'll go through the main components of distributed system. We'll start with communication, inter-process communication, how components of a distributed system communicate with one another. That'll be the first topic. Then we'll talk about processes, threads, and their scheduling. Okay? This will pick up from what you typically learn in an undergraduate course in operating systems, which is basic processor scheduling. Here we'll look at scheduling tasks in a distributed system. Okay? We'll talk about naming and location management. That will be a brief lecture. And then a good 4 or 5 lectures we'll spend on what we call canonical problems in distributed systems. Okay, so when you design any application that's distributed or any system that's distributed, there are many common issues that come up that you have to deal with over and over again. Okay? So what we will do is we'll abstract them out and we'll study them in the abstract. Okay? This could be things like synchronization, coordination. So there are a number of these problems that keep coming up: leader election, mutual exclusion, and we'll study them in the abstract, and then we'll see how they apply to different use cases. Okay? So that's a key component of the course where we look at those problems, and then once we go through that, we will talk a little bit about replication and consistency, another important principle that arises over and over again in distributed systems. And a related topic to replication is going to be fault tolerance. How do you handle faults in a distributed system? Okay. We'll briefly touch upon security in distributed system. I have de-emphasized this topic somewhat because now there is a graduate course in security that you can take if that's of interest. A lot of the topics overlap, so we will only talk about it very briefly. Okay? And then there will be several advanced topics that we are going to cover. There's going to be some coverage of middleware, but we'll also talk about the World Wide Web, cloud computing, energy-aware distributed systems, which is also referred to as green computing, pervasive computing, multimedia, mobile systems. So the last several lectures will be on advanced topics, which basically show you or give you an insight into how distributed systems are used in various different contexts, okay, various different scenarios, going from web to mobile, pervasive, and so on. Okay? So that is in a nutshell the topics that we are going to cover here. Okay? If you have suggestions on other things you would like to see, you can come talk to me. I'll see if I can accommodate some requests, because we have a little bit of leeway towards the end on how we tailor the content in terms of advanced topics. Okay? The first roughly 2/3 of the course just follows the book. Okay? Those are all basic topics in distributed systems. Any questions, comments about this? Okay, so I already mentioned the book. Okay, so that's Tannenbaum's book, which we will follow. The grading basically will involve, or the grade rather, will involve 3 things. There will be 2 exams, a midterm and a final. That's 20% each, 40% of the total grade. There will be 3 programming assignments. It says 3 to 4, but usually we only do 3 programming assignments. That's roughly 40% of your grade. Homeworks, which will be about 15%. For the in-class section, we'll have class participation points, which will be 5%. Okay? And for the other section, we will deal with that in a different way. Okay? So class participation basically means you should ask questions and have a discussion. The goal of the class is not for me to stand here and speak and you just listen silently. We would like to have back and forth where you ask questions and I can elaborate on concept. That's how you learn. You shouldn't just come and just let me just do all the talking. That's not the objective, which is why there's an incentive to ask questions, okay, which is going to be all in class participation. Okay. As far as the programming assignments go, this is a graduate level course, so we will just give you the specification of a programming assignment. You can use whatever programming language you want to implement it. Yes, you can make your choice of what is the right way to do it. Okay, there will be a lot of creative freedom that we will allow. Okay, so you can decide how you want to implement it and so on. Okay. So we don't require that you do it in Java or C, or but you can use Python, whatever you want to if you use some very obscure language, you should at least talk to me, because the TA has to grade it. Okay, so we can only do so much, but we will let you give you the freedom to decide how you want to implement it. Okay. The final exam is typically take-home exam. Okay, the midterm exam is a closed book, closed notes exam. Okay, traditional class exam, but held in the evenings. The final exam is open book, open notes. So you just hand it out. I hand it out. You hand it back in 24 hours later. Okay, that's how we have usually done it. That's what we will continue to do. Okay. One more thing is at the end of each week, I am going to hand out a quiz. Okay. This is more to do with the online section of to make sure the students are actually following along and not putting off viewing the course lectures. Okay. So the quiz will usually come out on Thursday, and it will time out on Sunday, which means you can take it any time between Thursday and Sunday. You are also required to go and sort of take the quiz. It will be handed out on Moodle. But as I said, this is really, I put this in place more to make sure the online section students who I don't see most of the time are actually keeping up. And the quiz will actually involve the 2 lectures from that week. Okay, so from your perspective, you need to make sure that you are following along also by coming to class and reading up on the material and so on and so forth. Okay, so there will be weekly quizzes, and because it's weekly, the total quizzes will not add up to a whole lot. Okay, so there will be no makeups given for quizzes. Don't come and tell me I have to go somewhere and I cannot take the quiz. It's okay. If you miss a couple of quizzes, not going to make any difference to your final grade. Okay, you shouldn't just blow off all of them. Okay, but if you just miss a couple of them, it won't make any difference. So feel free, if there are some scheduling issues, to not take a quiz once in a while. It won't make any difference. Okay, I'm not going to try to make extra accommodation for quizzes, because it's just too much trouble to do that. Okay, so that's basically how the course is going to be structured in terms of grading and so on. Any questions about this? Okay, so there is a mailing list which you don't have to worry about. In some sense, you're already on it. You should have gotten an email from me yesterday if you're registered for the course. Right, so that's basically used to send out course announcements and so on. Okay, the course does require an undergraduate exposure to operating system, because we are going to build off material that's covered in an undergraduate class. Okay. Now, if you haven't taken such a course, you can come talk to me. Sometimes people are, you are basically able to keep up, and sometimes you may have to do a little extra work. But I'm generally going to assume that you know what operating systems are, and you covered some basics in an undergraduate class. Okay, so that's the assumption that we will make, and most of the time I think just basic knowledge is good enough. Okay, but we do assume that. The other thing, of course, is you need to be able to program. Okay, this is a systems course. A substantial portion of the grade is going to be determined by the programming assignments. Okay, roughly 40, which is 40% of the grade. Okay, so you need to know good programming so you can deal with the programming assignments. So with those 2 prereqs, I think if you have those, then you should be good as far as the course is concerned. Any questions about these 2 requirements? Okay. Okay, so that's the background. Okay, I'm going to now start with the introduction to distributed systems. We'll talk a little bit about what they are, why should they interest us, and then I'll give a little bit of history and talk about various types of distributed systems. Okay. So distributed systems have now become very commonplace, given the emergence of the internet and so on. Practically most computing applications that you interact with on a day-to-day basis have become distributed in some shape or form, whether it's websites, systems like Google search engine, Amazon, peer-to-peer file sharing systems, social media. Take any of these, cloud computing, and so on. They're all examples of distributed systems. They differ widely in what they do, what applications they serve, and how they are built, but they are distributed. Okay, so So basically what we are seeing now is most applications that you see, computing applications, are distributed in some shape or form. So this is important to understand how they are built, how they work, because you may actually end up building distributed systems as part of your job or career someday. Okay? Or if not, you will actually use them. So knowing about them is also very useful. So it's useful to understand how real world systems work. And what we will do here is cover the basic principles, okay, because this is a core graduate course. So we start with the basics of distributed systems, and as I said, towards the end we have all of these special topics which will show you some or shed some insight as to how some of the specific systems were built using the basic principles we would have studied by then. Okay, so we'll start with the definition of a distributed system. So I'm going to give a very simple but very broad definition. So we'll assume that a distributed system is a set of computers that work together. Okay? It's a collection of independent computers connected over some networking, connected over a network or a communication medium that provides a coherent abstraction to its user, okay, of being a single larger logical system. Okay. This is a very straightforward and broad definition. In fact, it's somewhat overly broad because this definition is going to cover not only distributed systems but also what are referred to as parallel systems. Okay? A parallel system is essentially a single machine that has multiple CPUs in it. Okay? And you think about it, in fact, most computing devices that you have access to today are parallel systems because they are multi-core in some shape or form. Okay, even the smartphones that you get today have become 2-core or 4-core machines. Okay? Laptops are multiple core, servers are multiple core. So those are simple examples of parallel systems where there are multiple CPUs. They're connected together. The interconnect is the system bus. And so they can talk to the CPUs can communicate over the system bus. That's an example of a parallel system, and that the definition is broad enough to encompass that. Although I will distinguish what we use traditionally known as a distributed system from a parallel system. A traditional definition of a distributed system is the CPU is in its own machine. So you have multiple machines that communicate with one another to achieve some higher level task, rather than multiple CPUs within a single machine that communicate with one another. Okay, so some distinction between parallel and distributed systems. We will cover some aspects of parallel systems in this course as well, although the course is on distributed systems, because I gave this broad definition for a reason, because we will look at parallel systems and also distributed systems. Okay. So why design systems to be distributed? Why not make them centralized? So there are several advantages to designing systems in a distributed fashion. Okay? And there are several disadvantages also. Okay? Some advantages are listed here. First is it makes communication and resource sharing possible. Okay? If one machine can communicate with another machine, it can access the resources on those machines. The resources could be data stored on that machine or files on those machines. There could be any other resource. Okay? It could be a printer that's attached to that machine. If you actually share it over the network, you have a network printer. You can print over a network rather than requiring a printer to be connected to your machine. Any hardware or software resources that exist on a remote machine now become accessible to you, okay, over a distributed system. Okay, so communication is possible, resource sharing is possible. Communication takes many forms. You use communication applications like email, chat, and so on. And there are applications that talk to one another as well. Okay, and all of that is made possible by a distributed system. Okay. Distributed systems also give you better price performance ratio when you're trying to build large or high volume request volume applications. Okay. So if you have to build, let's say, a website that is going to be very popular, okay, and it has to service lots of requests, there are two ways to do it. One is to buy a large machine, okay, lots of cores, or maybe it's a very high-end machine, and run your website on that machine. Okay. It has lots of RAM, lots of cores, so it can service lots of requests. Okay. That machine is probably going to be expensive to buy. Okay. The other way is to buy lots of little machines, cheap machines, and connect them over a network and run different replicas of your website on each of these machines. Okay, that's another way to scale up and build a higher scalable application, is to have smaller machines that are interconnected over a network, and your application is distributed across those machines. Right? And the point that we will want to take away is doing the latter gives you better price to performance ratio. You can build the same application, service the same number of requests at a lower price point than building a giant machine or buying a giant machine. Is that clear? You get better price performance ratios because you can buy the smaller machines and then scale up that way rather than buying larger machines and scaling up. Yet another advantage is reliability and scalability and fault tolerance. If you have multiple machines and you build your application well, the failure of any one machine will not take down your entire application. Application continues to run as if nothing has happened. Maybe its capacity of how much it can serve goes down a little bit. Okay? This is not true in a centralized system. If your machine goes down, your application stops. Okay? There is no way around it. In a distributed system, that does not have to be the case. You can handle failures in a transparent manner. Okay? Some fraction of your nodes may be down. Application is just going to continue to run, assuming you have built it well, assuming there are no single points of failure in your application. Of course, you could not write your application well, even though it may be distributed, and it will fail if one component goes down. But if you do it well, you don't have to have a deal with this problem. Okay, so it has higher reliability. It's also better scale. It's the only way to actually scale to very large systems is through distributing your application across over lots and lots of machines. Okay, so practically any large web service that you see, okay, Google, Amazon, eBay, any of Facebook, any of these services that you see are distributed across tens of thousands of servers. Okay, in some cases, they may be distributed across millions of servers. Okay, so that's the kind of scale that you need if your user base is global. Okay, if you're building an application that's going to service 100 million users, okay, this is the only way to build your application. You can't buy one large machine. There is no such machine you can buy that's going to service such a large user base. You have to fundamentally distribute it across machines, across sites, not even across a single site, because your user base may be global, multiple continents. You have to put servers on each of those continents, each of those countries. Okay? So this is basically how you are going to scale to very large high-end systems, is to distribute your application over lots and lots of servers. And we will see when we talk about either the web or cloud computing, how do you build some of these systems, okay, from a basic principle standpoint. And one last advantage is it has the potential, gives you the benefit of incremental growth. So this is something that is may not be clear when you are designing an application. Let's say you are a game designer. Okay? You want to write a new game and release it. But when you release it, okay, so let's say there is a game server that the game is going to run on, and your users are going to come and access it through some device that connects to a game server. Okay, but when you write the game, you have no idea how popular your game is going to be. Maybe it will take off like wildfire and you will have a very large user base, and maybe it will flop and there will be nobody wanting to access your game, but you don't know. Okay? But when you release it, you have to ask, so how many servers will you run this on? Will you run it on one server, 10 servers? Okay, you don't know how popular your game is going to be. Okay? So what distributed system, if you allow you to do, is to plan for incremental growth. So maybe you write your application, the game server well, and you start with 2 servers. Okay? And then you watch your user base grow. If the user base starts growing, you can add a 3rd server. Okay? You don't have to throw away the first 2 servers and buy some bigger machine. You can keep adding servers as you go, as the popularity of your application keeps growing. Okay? So what this means is, initially when you don't know, you don't have to make a large upfront investment. Okay? You can buy smaller amounts of hardware and then incrementally add hardware as you go along. This is much more cost effective than ending up with one big server where you put this game expecting it to be popular and it doesn't take off, and you wasted a lot of money buying a large server when your application is not being used by anyone. Right? So incremental growth is actually very important benefit in many scenarios where you can grow your application over time as your user base grows, and you don't have to put up all of your capital investment upfront because you don't know how much to invest in to begin with. Yeah, another important advantage, that's how most applications actually grow. Whether it's Google or Facebook, they all started someday on 1 or 2 servers, and now they are at 1 million or hundreds of thousands of servers to million servers. They continue to grow in this fashion. Okay? Important benefit, but often overlooked. Now, those are all good things, but with any advantage, there is going to be some disadvantage. You don't get something for nothing. Okay? So there's no free lunch. So disadvantages of distributed systems are your application design is fundamentally more complex. Right? Writing a distributed application is going to take more work, is going to be more complex than writing your single Java, one thread Java application, centralized application. Okay? Application design becomes more complex. Programming languages have to also evolve to handle needs of distributed applications. Okay, you will either have extensions or your programming language itself has built-in features. Okay, all of them make your programming a bit more difficult. Okay. Network connectivity is obviously essential and key. If a network goes down, your distributed system will not work as it is intended to work. Okay. And the other big issue that comes along with this is security and privacy. Okay, the moment you make your application distributed and accessible over the internet, okay, you have to deal with all the malicious people in the world trying to hack into your application and trying to do bad things to it. Okay? So, and you see all of these breaches, data breaches happening all the time because the large complex systems have bugs in them. And hackers try to exploit these bugs and then exploit the system itself by either stealing data or using it for nefarious purposes. Okay, so security and privacy becomes a big challenge. If you had a centralized system that was not connected over a network, obviously there is no security threat from the internet because nobody can access your machine. But as soon as you make your application network, you have to deal with this issue. Okay. So we are going to look at security and privacy issues as well. But as I said, we will look at it very briefly because there's another course that deals with this topic. Okay, so at a very high level, the way you design your distributed system is actually very important from a usability perspective. Okay, as a distributed system designer, you have to often ask, what is it that you are going to expose to your users and what are things you want to hide from the users and not necessarily make them deal with it. Okay? And depending on these design decisions, there will be implications on usability. Okay? So there are many design decisions you have to make when you design a distributed system. And depending on whether you hide something or expose something, you get basically various axes of transparency. Yeah, transparency essentially means, is a property made visible or is it hidden? And I'll give you some examples. So we'll not go through all of these. We'll actually encounter them as we go along in this course. But just to give you an example of how you can design the same system in 2 different ways, let's take replication transparency. So replication transparency basically says that you may hide the fact that a particular resource or an application is replicated on multiple servers. Okay. Now, depending on whether you hide this fact or expose this fact, you may get 2 very different system designs. Okay. So I'm going to give you an example that you can easily relate to. Let's take the Google search engine. Okay. The way you access it, you go to www.google.com and you get a search box and you type in a search query. Okay. Now, behind this search, this very simple interface is a very large infrastructure. Okay? Tens or hundreds or thousands of servers that are actually collectively servicing search requests. Okay? All of this is hidden from you. Okay? You simply go to this one URL www.google.com and you send your search query. Something else is going to figure out which of those 100,000 servers will this query go to. Okay, how is it going to be processed and how the results come back. All of that is completely transparent to you. Okay, so this is replication transparent. The fact that your search engine is replicated is not made visible to you. So you can use it using a very simple, easy to use interface. Okay? A different design decision could have been that you expose the fact that there are all these replicas. Okay? So now you have to decide which replica to go to. So you may say www.1035.google.com. So I'm going to that server. Okay, and then I'm going to send my search query to that particular server. You could have made a design decision and said, let the user pick which server they want to send the search query and let that search query be executed by that server. Clearly, that would not have been a good design decision, but that's where you made the fact that there are replicas in the system visible to the user, and you're making the user pick which replica to use to service your request. Okay. Now, in the case of search engines, obviously it doesn't make sense to make that replica visible to the end users, but there will be other scenarios where you have to decide that should I make something, the fact that there are replicas visible, or should I hide it and deal with how requests get mapped onto replicas internally by the system. And depending on what you pick, you may either have a replication transparent system or a system that's not replication transparent. Okay. Now, for each of those other properties, the location of your application, whether the resources migrate or not, whether there is concurrency in the system, whether components fail or not, all of those could be either transparent, which means it is handled by the system transparently to the user. The user doesn't know, the user doesn't have to deal with it. Those properties are handled internally, or are you going to expose it? If something happens, like failure transparency says, if I am connected to a particular server, okay, and it's servicing my request and the server goes down, will that actually be made visible to me? Will I get an error saying something went wrong, please try again later? You often see this message on a website. Okay? Or you could design your site to say, I know the server failed, I will have some other server take over and continue. And the user doesn't even have to know that the server failed. That would be failure transparent. Okay? So there are many design decisions you have to make. And ideally you want to say, okay, I will make all of these things transparent to the user. I, meaning the system, I'll write my system to deal with all of that. But be aware that that will increase the complexity. Okay, if you do more yourself, that means like you have to put more code in your system to deal with it, right? So this is going to be a design trade-off. Some things may be okay to expose, others you should hide to keep your system usable. Okay? So these are all decisions you have to make. Okay, I'm not going to go through all of those properties, but I just wanted to make this. Yes.
Apart from the trade-off of complexity, is there any trade-off between these? I mean, like, is the access is trade-off with congruence? Let's say, this is an example. Are there any trade-off in between them?
Are you asking are there trade-offs between properties here?
Yes.
So each of those properties are somewhat independent dimensions. So now it may be that if you make some property transparent, it may have implications on how you deal with something else. So for instance, if your system is not replication transparent, which means you are actually asking the user to pick a server to do something, it may be harder to make it failure transparent because I have chosen that server. If that server happens to be down, you can't make it transparent too. And so there are some implications like that, but by and large they are somewhat independent. But there will be occasionally some of these properties may have some couplings that you have to think about. Okay. There's a question somewhere there. Okay. So anyway, we will come back to lots of these properties throughout the course. Have discussion on what a particular system has chosen to do and why it chose to do that. Okay, but this is something to keep in mind. Okay, so completely different dimension of distributed systems is whether they are open or closed. An open distributed system is one where the interface of how you interact with that system is open and published. Okay. The source code may also be available, but that or may not be available, but at least the interface and the services and the semantics are openly published. So what this allows you to do is, if you know how to interact with a particular component, its API is already published, then you can write other components that interact with it and build other useful tools with it. Right? There are many systems where the APIs are published. So Google has an API, for instance, where you can, the Google Maps API, for example, is a published API. So if you want to incorporate a map into your application, you simply use the APIs to request the map for a particular location, and you can embed that map into your other application. So now you could build other useful services by using parts of some other distributed system. In this case, it would be the Google mapping service. Okay? But there are many other systems that do not expose their APIs. Okay? They are closed, which means you cannot write other components to interoperate with them. Okay? Only the designers of those systems could add additional components or functionality to their own system. Okay? Now, by and large, systems are becoming more open because the designers of the system realize that by exposing APIs, they enable lots of other functionality, which makes their services more popular and more used, and hence they can make more money. And so on and so forth. But not all of the systems out there by any means are open. Okay? An open system is one that, as I said, exposes its interfaces, publishes its APIs, exposes the semantics of what happens when you make certain calls, and so on and so forth. So interoperability and portability are the two biggest benefits of making a system open. Okay, there's also extensibility, which means open systems. The system is open, you can extend it if the source code were also available for, say, not just the interface. Okay? So that's something to keep in mind, and you will encounter many systems that are open, and we'll use them in this course. Okay? Now let's talk a little bit about scalability. Okay, so this is basically where we are going to ask the question, what's the fundamental difference between a centralized system and a distributed system from a scalability perspective. Okay. So when you say centralized system, okay, so there are 2 or 3 different ways of how your system may be centralized. You may have a centralized service, which means there's a single server for all of the users of that service. You may have centralized data, which means all of the data that your application uses is on one system. Okay, data is centralized. Or you can have centralized algorithms, which means that your algorithm itself is centralized and running on one machine. Okay, so you can have any of these combinations or some subset of those combinations. Okay, centralized service should be clear. It's a single server to service all of your users. The moment you max out the capacity of that single server, you will not be able to grow or scale your application beyond that. So the scalability issue comes up when the number of requests that are coming into your service exceed the capacity of the server that the service is running on. Okay? A distributed service will not have this limitation because it can run on multiple servers. So you can harness the capacity of multiple servers, which means you can service more users than a centralized service. Okay, fairly simple. Okay, centralized data is somewhat more interesting because in centralized data, there's one copy of the data and it is stored on one machine. Okay. So you are somehow limited to the I/O capacity of that machine to access that data. Okay. You are also limited that if the machine fails, your data goes away. Your data is lost. So there are 2 ways to relax this assumption in a distributed scenario. Okay. One is partitioning the data, the other is replicating the data. They are 2 slightly different things. Okay? And you can use this example here to understand the difference between the 2. So the example here is you can use a telephone directory, an online telephone directory. You build it in a centralized way, your entire phone directory, okay, all of those records are on a single machine. Okay, so now you are limited by the capacity of the machine. So how do you relax this assumption? If you do partitioning, That basically says that you are going to take that data and you are going to chop it up into pieces and you'll store each of those subsets on different machines. So you can say, I will partition it into two halves. Okay, all the telephone directory entries from A to F will be on machine 1, G to Z will be on machine 2. Okay. More scalable, you still have one copy of the data, but just that the data is now partitioned into two machines. It's still distributed. Okay. That somehow relaxes the centralized limitations. Okay. An even better way is to replicate. Okay. Basically, not only do you want to partition, you want to have more than one copy of the data. Okay, so you basically replicate your telephone directory on multiple machines. Now you can harness the capacity of all of these machines together. Okay, so those are two ways by which we can deal with this scalability problem of centralized data: partitioning and replication. Okay, you will often see systems will only employ partitioning, not replication, because it's the simpler thing to do. When you have replication, although you can scale more, there are bigger problems because you have to deal with consistency. If you have multiple copies of your data floating around in your system, the moment you update one copy, all the other copies become stale. Okay? So you have to now implement what are called consistency algorithms that take the update you made and propagate them to all of the replicas so they're all in sync with one another. Okay, until that happens, so requests coming to one copy will or one server will see the newer version of the data, and requests going to other replicas will see older versions of the data. And this can often cause problems, as you can imagine. Okay? So replication sounds better, but you have to deal with the consistency problem whenever you are replicating. With partitioning, you will not have this problem. Okay, you are scaling by chopping the data into smaller and smaller pieces and distributing each of those chunks onto a different server. But there is always only one copy of every record. Okay, so if you update it, any requests, subsequent requests come in, they see the updated version. You will never see stale data. Okay? So you will see that many systems try to scale by partitioning, not replication. But in the end, I think partitioning can only go so far. Okay? The limit is where each record is stored on its own machine. You can't scale any more than that. And beyond that, you have to replicate. Okay? So, and then you have to deal with the consistency issue. Yes, question.
Combination of partitioning and replication be used to solve the problem with partitioning.
Yes, so you can do combine partitioning and replication. So here is some example. So let's say these are two machines, and you have, if you had centralized, all the data would be here. Okay, if you had partitioning, you chop it up into two pieces, and the top half is here, lower half is here. You can also replicate this by putting this also here. So now there are two machines. Okay. And you can have pure replication where all the data, the entire telephone directory is on. So no partitioning, but all the data is also replicated. So you can have any combination of this. Okay. Centralized algorithms are a little more subtle in that the algorithm is running on a single machine. So it has some limits on how much it can scale. Yeah, you can distribute this algorithm by having your algorithm actually run on multiple machines, and these components actually talk to one another or coordinate with one another to achieve some higher level goal. Okay. Routing is an example. There are many examples of distributed algorithms that we will encounter in this course. When you take a centralized algorithm and you make it distributed, you have to deal with how are these pieces going to coordinate with one another. A distributed algorithm is not the same as a replicated version of a centralized algorithm. Okay? So keep the two in mind. So here is the difference between the two. It's the same distinction as partitioning and replication of data. Okay? So let's say you have a program that's running here. Okay? You take the same code, okay, and you run it here. Okay, now you have two machines running exactly the same code. This is simple replication. Okay, the algorithm hasn't become distributed. You simply took the algorithm and you're running the same. You wrote a program that implements it. You run it on two machines. Okay? A distributed algorithm, on the other hand, is basically a different implementation of the centralized algorithm where you take the algorithm, let's say your subtasks in your algorithm, and you write it such that some tasks are done here and some tasks are done here, and these two components talk to one another, they coordinate with one another or communicate with one another to implement the same function as the original centralized algorithm. Okay? This is somewhat equivalent to partitioning, because you took the larger algorithm, you said these are several subtasks you have to do. I'm going to take these subtasks, run them here, these subtasks, run them there, and they will communicate with one another and still do whatever the centralized algorithm. So that's the same as taking the data and partitioning. This is a distributed version of a centralized algorithm. Replication, on the other hand, says you take the same code and you run it on multiple machines. That was the same as taking and replicating the data. Okay, so you have the same distinction when you talk about taking an algorithm and distributing it. You can have replication or you can have distributed implementations of an algorithm as well. Again, we'll encounter some of this as we go along. Any questions here? So these are some very high-level principles to keep in mind when you design a distributed system or a distributed algorithm. Okay? Some of this may not make sense at the moment because we don't have the right context or the background for you to appreciate why I'm saying. But I'm going to state the principles, okay, and try to explain it or give some very high-level intuition. But as we go along, we'll come back to these principles and then get a better understanding of why these principles make sense when you want to design truly scalable systems, okay, that don't have any bottlenecks that a centralized system would have. Okay? So the four principles are no single machine should have complete state information. Okay? State is what information you need to implement your application, whether it's data, whether it's memory state. If you actually put all of the state on one machine, okay, you have a centralized implementation. If you require all of the state to be known in order to make a decision, you are going to have a fundamental bottleneck where every component of your application has to talk to lots of other components, query them in order to understand what they are doing to make its own decision. Okay. So no machine should not need, or a single machine should not need complete state in order to implement this decision. That would be a right way to implement a decentralized algorithm. Making decisions based on local rather than global information is another good design principle. If you actually need global information, you need to know what is happening everywhere else in your network in order to make a service a request. That is not going to scale very well. On the other hand, when a request comes in and you use whatever that machine knows locally in order to service that request, that is going to scale much better because there's less communication between components. Okay? Very simple example is, let's say a search query comes into a search engine. Okay? If all of the information you need is available locally and you can service that request without talking to any other machines, you are going to serve it better. But in order to service the search query, if you have to talk to 20 other machines and make that decision, that's going to impose higher overheads on your system. Okay, that will scale much less. Okay. So making decision based on local information, okay, not having a single failure take down your entire system. What that means is there should not be any single points of failure. A single point of failure is some aspect of your larger application that is specific to only one machine. Okay, and if that machine goes away, there is no way for some other machines to perform that task. If you have any single point of failure, if that component goes down, even though other components may be replicated, you are going to basically have your system go down. Okay. And basically the reason I say this is when you have large distributed systems, it is not that every component is going to be replicated or distributed in the same way. You will see what is that component trying to achieve, and you may make different design decisions for that component as compared to some other component. Some may be highly replicated, others less so. Some may be partitioned, others may be replicated, and so on. Okay, you don't make the same design decisions for everything because large systems are very complex. You basically design them as components, okay, and then you make different design decisions. So if you don't have a single point of failure, you will actually scale much better. Yeah, otherwise, that component failing will take down your system. Okay? Last principle is you shouldn't require a global clock. Okay? What this is a fancy term for saying you shouldn't require perfect synchronization in your system. We will see that there are many distributed systems that make decisions based on timestamps. Okay, they will, when request comes in, they'll timestamp it. The request will be sent out to some other machine. It will do something to it and so on. If you actually use these timestamps to make decisions, then you're fundamentally requiring that the clocks of all of the machines are synchronized with one another. Otherwise, if one machine timestamps a request, saying request came at noon and sends it to other machine, and that machine has a clock that is offset, that timestamp is meaningless. It doesn't know what to do with it. So if you use timestamp, then you're fundamentally assuming that there is some synchronization that's run that synchronizes all the clocks, so you can reason about other machines timestamping some events or some requests and so on. Okay? But the point I'm trying to make is that if you design a system so that it does not rely on that property, you will scale much better, because as we will see when we talk about clock synchronization in a few lectures, that there is no perfect clock synchronization algorithm. All clock synchronization algorithms are approximate. They give you some precision, but there is always going to be an error. So you will always get tripped up in some corner cases. Okay? So most of the time it may work, but for some very specific cases your algorithm may not work, because clock synchronization can never be perfect. Okay? So if you design your algorithm to not depend on this property, and you may not be able to understand how to do that yet, that's okay, don't worry about it. When we talk about clock synchronization, we'll look at this again. So no global clock is always the right way to do it, because you cannot actually have perfect synchronization. So those are 4 high-level principles. I try to give a little bit of intuition. Maybe not all of it is clear, that's okay. At this point, just take this as axioms, but when we talk about the principles, we'll come back and we'll understand why these make sense. Any questions on this? Okay. Last few bullets here talk about techniques that you could use to design your application. They are not principles themselves. Okay? You can use asynchronous communication. We'll see that asynchronous communication applications that use asynchronous communication can scale better than those that use synchronous communication. When we talk about architectures of web servers, we'll come and discuss this in more detail. Distributed versus centralized, we already talked about. The more distribution you have, the more you can scale. Okay? And caching and replication is another property that's used often in distributed applications or systems. Okay, replication is very common. Caching is another way to do replication without replicating the data itself. Okay? So you basically may have one copy of the data, but you have lots of caches where the caches hold the replicas. You don't replicate the data itself. So you can always use caching as a way to scale if your data itself cannot be replicated in some shape or form. Again, we'll come and talk about caching in many different contexts, including web caching and caching in distributed file systems and many other scenarios. So those are just techniques that are used. They're not principles per se, but techniques used to scale your distributed system in some shape or form. Okay. Okay, so I'm going to now do a quick history lesson in some sense of a distributed system as to how they evolved and where we are now with respect to what distributed systems looked like in the 80s. Okay, so 30-year history in 2 slides. Okay, so basically the earliest distributed systems used what was called a mini computer model, where you had a machine, okay? You could connect to that machine over a dial-up phone line, okay? And communicate with it and then disconnect. The most popular application that used that model was actually email and news groups. So this is how email used to work. If you have to send email, you send a mail, it sits on your local machine. periodically your local machine will actually make a phone call to another server somewhere. Okay, and over a modem, it will then send over your email, and the email will be delivered. Okay? That's how very early forms of distributed applications were. Because there was no internet, there was no persistent connectivity. Okay? You basically had to dial, connect to a machine, communicate, disconnect, and then after some time dial again. Yeah, this is sort of pre-internet where you had a persistent connection which is always on, so you can send or receive whenever you want. That was not the case, but early machines used this mini computer model. The other way these mini computers were used is you had this terminals, which is basically where you think of them as very low-end PCs, and the terminals were all connected to this one machine, so multiple users could log in, run multiple processes, and so on, or communicate with one. Okay? Very early forms of distributed system. A lot of processing was local, but you could get accesses to remote data or files through this communication that was made possible. Okay. So there was a big jump when you went from the mini computer model back in the 80s to the workstation model. Okay. So as hardware kept getting cheaper, it became possible to give every user a workstation. A workstation is, so think of it as a glorified PC. And works, so basically now every user had a machine. These machines were all interconnected on a LAN. Okay. This allowed a whole new class of distributed applications to be deployed and used. Okay. We'll come through some use cases subsequently, but in the workstation model, distributed file systems became very popular. Users could freely share their files. You could access remote files because all the machines were all connected on the LAN. Yeah, you could also do some more advanced things like process migration. You could start a job or an application on your local machine, okay? And if your local machine was overloaded for any reason, this job could hop onto some other workstation that was idle. The process would itself migrate and run somewhere else, okay, where it could finish faster, say. Okay? So you had systems that could do these kinds of or implement these kinds of mechanisms. Share data, have processes that keep hopping from one machine to another to find faster or less loaded machine to migrate. So that was the workstation model. It's still there today. Workstations are essentially laptops now, but that's essentially where they came from. Okay. Concurrent trend to the workstation model was the client-server model. The workstation model, all machines are identical in some sense. I mean, every machine is equally equipped in terms of its hardware capacity. Okay. Client-server model essentially distinguishes between a client machine and a server machine. The server machine is somehow assumed to be more powerful or more does more than the client machine. Okay. And this is fundamentally a request-response style scenario where clients send requests to servers, servers process requests and send the response back. Okay, so this enabled a new class of applications which were request response. Okay, notice that sharing files is not necessarily in that category. Okay, request response are web servers, sprint servers, and so on. You can submit a job to a server, the server processes and sends back a response. Okay. So this model coexists with the workstation model. So you can have workstations, but you can also have server machines. Most of the time you do your work locally, but once in a while you may send off a request to a server and then server processes that request. Okay. So, and the most popular users of these servers were file servers, print servers, database servers, and so on. Okay. And clearly this model is still with us today as well. Okay. And this is the most common way of building distributed applications. Okay. Now, as hardware kept getting cheaper and cheaper, there was yet another model that arose, which is the processor pool model. Think of the processor pool model as a client-server model in which the server has a pool of processors or a pool of CPUs. Okay? So it's a big server with lots of CPUs, a pool of CPUs, and then clients are simply sending requests to the server, and the server decide which processor in the pool will service your request. Your server may have, let's say, hundreds processors. Okay. You simply send off a request, say, here's the request, service it. You don't say which CPU to send that request. You simply submit it to the pool, and then some software that sits on the server will say, here's a request, let's CPU 25 service it, because that's the one that's idle at this moment. So it will be sent off to that processor. The processor will service your request and you'll get back a response. Okay. So this model became popular as an alternative to the workstation model. Okay, this is also called the thin client computing model, where you had a more powerful server and your clients became less powerful or somewhat dumb. Okay, so you could have what were called diskless terminals or very low and thin clients, where most of the computing was done remotely. You would send off a request, this big pool of processors would then service your request and send you your response. Okay. Thin client are still with us today, and so are processor pools in some specialized scenarios. It's just a variant of the client-server computing where the client is more stripped down, the server is more powerful. So more work is done by the server, less by the client. Okay. So those models, the client-server model, the processor pool model, and the workstation model have evolved into several new directions today. Okay. So they are just variants of those models that I just put up previously. So cluster computing is essentially, as we have it today, is essentially a form of the processor pool model. Okay? The cluster computing, you have a rack of servers. That's a cluster. You can submit jobs to this cluster, and the cluster will then service this request and send back a response. Okay? It could be used for batch processing, where you submit simulation jobs, or it could be used for interactive processing, where the cluster runs a large web server or a database server. So it's a form of a processor pool where the processors are essentially CPUs on independent servers that are on this cluster. Okay, so cluster computing and data centers are basically an evolution of cluster computing. A data center is a large warehouse which has a very large cluster. Okay, so it's a facility with lots and lots of servers that form a cluster. Okay, so cluster computing and data centers are an evolution of these trends that I talked about previously. Okay, grid computing, same thing. Okay, you can take clusters and then connect them over a wide area network. So now you have what is referred to as a federated cluster. Okay, it's logically a bigger cluster, which is a union of smaller clusters that are connected over a WAN. Okay, and these clusters can also hand off jobs to one another. You submit a job locally. If this cluster is overloaded but some remote cluster has capacity, that job will be forwarded to that remote cluster. Okay, that's what grid computing will allow you to do. Okay, so this is a more distributed form of cluster computing, which is grid computing. And then you have today's modern systems which basically run on distributed data centers or WAN-based clusters. So Google, Amazon, eBay, Facebook, they all are, as I was mentioning, global scale applications. So they don't run on single cluster or a single data centers. Okay, these applications are spread across many different sites across the world. Each site is a data center with a large cluster. Okay. So it's yet another evolution of cluster computing where there is more distribution. The distribution is now global. It's across sites. It's geographic. Okay. So when a request comes in, somehow it gets forwarded to the nearest site. Okay. How that happens, we'll see later. Okay. So when you send off your search query to Google, it is forwarding it to some local data center that's nearby. Okay. If you are a user in Asia, your search queries go to the Asian sites. If you are a user in North America, your search queries go to a North American site. So this is basically a global form of your processor pool model where you submit a request and somehow it gets mapped to some server and some CPU somewhere. Okay, but now at a very large scale, a very distributed fashion. So that's basically a distributed data center, somehow related to grid computing but used more for interactive application. Okay, and then you have the basically evolution of this model into what's called cloud computing. Okay, so cloud computing are nothing but data centers that have clusters and servers that you can rent rather than buy. So rather than building your own, you lease from someone else who is willing to give you servers or storage to rent. Whether you rent hourly or monthly depends on the billing model of your cloud data center. Yeah, but you can basically rent for short periods of time. Rather than buying, you rent. And in some cases, renting will be cheaper than buying. And we'll come back to cloud computing as well. And even in some programming assignments, you will see what are the advantages. But it's simply an evolution of this trend towards more data centers, more distribution, and so on. Okay, and related topic to cloud computing is virtualization. And we'll see that both cloud data centers as well as other forms of modern data centers use yet another technology called virtualization that allow you to take one server and slice it into smaller virtual servers. Okay, so one physical server looks like a collection of smaller virtual servers. Each virtual server is exactly like a physical server, except that it has some fraction of the resources that are on your physical server. We will spend an entire class or two on virtualization as well, so that you will get a better feel for how you can do some of those things. But it's yet another trend that has basically made cloud computing, virtualized data center, all of those feasible. So that's basically a 30-year history of how systems have evolved. And again, that's very brief and very high level. Some of these we will go into in more detail. Okay, so last few things I wanted to say is this trend has continued to sort of evolve, and you have now distributed systems that you don't even think of as computing systems anymore. Okay, so there is, as hardware has become so cheap that you can now put microcontrollers and network interfaces on practically anything you want, okay, to a point where you don't even think of these devices as computing devices. So you have home networks where you may have a digital video recorder, media centers, your smartphones being a good example. Okay, you have basically 2 cores, 4 cores in them, multiple network interfaces, full-fledged computing devices that are basically just an extension of what you see in distributed computing. You're computing in your cars now that are coming up. There are more microcontrollers in a typical car than you would imagine. They are all networked, they all work together to allow your car to do its function, do whatever it does. And then you have these tiny sensors, which are also very resource constrained distributed system. You can put these sensors in all sorts of devices for all sorts of different functions. And these sensors perform a very specific task. They have a microcontroller and they have some network interface that allow them to communicate with some other system. And that's just an evolution of distributed system. So there are many different kinds of sensors that you will see. Sensors that monitor the environment, sensors that monitor that are designed very specifically for many different applications. Health is a good example. Okay, so you can buy all sorts of devices that monitor all sorts of health parameters for you. Right, so I have one here. So this is a small device that measures how many steps you walk every day. Okay. It has a Bluetooth interface, so it can talk to your phone. Okay, so your phone can then take the data that it's recording and then upload it to some server somewhere. And then that server will then show you a history of how much have you been exercising enough, have you been walking enough, and all of these things. Because you have sensors like this that monitor heart rate, that monitor all sorts of different things. Right? Your glucose levels, if you're a diabetic patient, for instance. So you don't think of these as computing devices, neither do you think of them as distributed systems, but they are in some shape or form. Because computing has become pervasive. You have these computing devices embedded in lots of different things. And there is networking also available for cheap, that you can now have very interesting types of distributed systems that you don't think of your traditional client server computing. And this is something that we will also look at in some detail in one of the later topics in the course. Okay? Having what we call distributed pervasive system, which is more sensors and highly resource constrained devices that are part of some larger application. Okay, so I have maybe 5 minutes. Are there any questions on this before I move on? Okay, so I'll do a quick run through some operating systems concepts. I won't get through all of the remaining slides, but we'll continue next time. Okay, so I also wanted to talk a little bit about evolution of operating systems. As systems themselves and applications have gone from centralized to distributed, operating systems have had to evolve in order to manage the machines that these applications run on. So OSs themselves have gone from uniprocessor operating systems to multiprocessor operating systems to distributed operating systems. So I wanted to talk a little bit about that evolution as well. Okay. So uniprocessor operating systems, I'm assuming most of you are familiar with. Okay. So an OS is basically a system software that runs on your machine that manages the hardware resources on the machine. It provides an easier to use abstraction for the users. So you don't have to deal with low level hardware details of the memory on your machine or where data is stored on your disk. All that is handled for you by the operating system. So its job is to basically be a resource manager, to manage the resources, provide easier to use abstractions that are easier to use. Now, uniprocessor operating systems are operating systems that run on single processors. So that's how they were built in the old days. And there are different ways to build them. Okay, one way is to have what is referred to as a monolithic OS kernel, where all of the functions of your operating system runs in one kernel process. It's one piece of code that runs on your machine, and it does all the tasks that the OS is responsible for. Okay, this is one way, an early way of how uniprocessor operating systems were designed. Okay, let me show you a different way of doing the same. Okay. A completely different way of building a uniprocessor operating system is what is referred to as a microkernel architecture. In a microkernel system, the base kernel is a very tiny kernel. It implements very basic features. The basic features are protection and inter-process communication. That's all that the kernel will do. And all the other jobs that the operating system typically does are implemented as user processes that run outside the kernel. So here is an example. Here's a file server. It's not part of the kernel anymore in a microkernel world. It's actually its own user process. Okay, here is the CPU scheduler. It runs as its own process. Here's the memory manager, virtual memory manager. And here is an application. So the application now, when it interacts with the kernel, it will go to the microkernel, but the microkernel will forward its request to the right component. Okay, so in a microkernel architecture, essentially you've taken the functions of your OS kernel and distributed it across independent processes that run as application processes. And the kernel itself is very compact, it's very small. All it's doing is enabling efficient communication between all these components. It's a very different way of building an OS kernel. From the monolithic world where everything is in one process, kernel process, now your OS has become multiple processes that collectively work together to achieve some task. Okay. Now there are advantages and disadvantages of this architecture, and I'm going to mention them and then stop here for today. Okay, so the advantage here is this is highly modular. Okay. If you want to implement a new file system in this microkernel architecture, you simply take this part, you remove it, and you put in a new process that basically uses the same APIs, and you have a new file system. You don't even have to know what else is there in your kernel. Okay. In the monolithic world, you actually have to look at the entire kernel code, understand where is the file system piece of it, and then when you change it, make sure you don't break some other pieces and so on. Okay. Much harder to write new functions into the kernel. This is much easier because each part is separate. You don't actually worry about what's happening here when you implement it. There is some API that you use to communicate. So long as you deal with that API, you can make local changes without having to know what else is going on. Okay. So it's more, from a software engineering standpoint, it is more modular. Okay. And some people will claim that it's also more secure because if there is a bug in the memory manager, you can't use the networking component to access it because they're separate address spaces. In a monolithic kernel, a bug in one part of your kernel is exposed throughout the kernel. Okay, any other function can access that function and exploit that one. Here, because there are independent address spaces, you will get a better form of security. So those are two advantages, and then the main disadvantage here is efficiency. Because your kernel is now partitioned into multiple processes, right, what used to be a function call inside your kernel process becomes an inter-process communication message that goes from one process to another in the microkernel. Okay. Your CPU scheduler could have simply called in the monolithic kernel a memory manager and said, here's a new process, allocate some memory. That's a function call. Okay. It's very inexpensive. Function calls are cheap. It's basically call from one function to another. Here, one process would literally have to send a message to another process which goes to the microkernel, is delivered here, process, send back a response. Okay, so that's going to have substantial overheads, which will slow down the functions of your operating system. Okay? So the main criticism of why microkernels and why they really never took off is efficiency. There are lots of advantages, right? But the efficiency is what killed this from going mainstream. Okay, there are still research kernels that use the microkernel architecture. In fact, early versions of Windows and even Mac OS X today have some elements of microkernel. They basically started with a microkernel architecture. Then they realized that performance was so bad that no users wanted to use your product. So then they said, how do we speed it up? Let's take this part which is critical, add it back to the kernel. Now that part is going to speed up because this inter-process communication is. So more functionality was put back into the kernel, making it look more like your old monolithic kernel. Okay, so this is basically how they evolved. So more and more stuff got put back in. So now there is what used to be a microkernel just looks like a regular monolithic kernel. Okay, just a quick history lesson of this was tried in commercial operating systems, both OS X and Windows NT, but did not work for efficiency. So my monolithic kernels are still what is widely used in terms of commercial operating system. They've gotten somewhat modular in how you write code. They're not as bad as I made them out to be, but they're not as clean in terms of implementation as microkernel. Okay. So we'll stop here today. Next time I'll continue this discussion, talk about multiprocessor and distributed operating systems before we go off to the next lecture. Okay, next topic rather.